So in section 14.7, we looked at an outline for finding the extreme values of a function z is equal to f of xy. And we know that the steps are to first find the critical values of the function z is equal to f of xy. And the most often thing that's going to happen is that you need to find the gradient of that function equal to 0. Okay, and the purpose of this first step is to essentially you have a function of two variables, and we know that that is some sort of surface. Okay, now this surface might have some little dips in it, right? So maybe the surface dips down here, and then over here there may actually be a little hilly part. And then there could be some places here where, maybe it goes up in one direction and goes down in another. So you have like a nice little place where you could camp on this surface if you wanted. Okay, so here what we're looking for is a critical value. So if the gradient is equal to 0, recall that the directional derivative of the function at a point P that's defined in terms of the gradient of the function at the point dot producted with u. So if the gradient of the function at the point P is equal to 0, the 0 vector I should say, then you know that the directional derivative at that point P will be 0 in all directions. U. So what we're essentially trying to say is that we're looking for these points on the surface where the function is essentially flat in all the different directions. So we first need to find these critical values, and then once we identify the critical values, we can then do the second derivative test. Okay, so the first thing we're going to do in this video is just specifically to focus on critical values. Okay, and it might be helpful to just consider an example. Okay, now one of the things that we're going to be looking for are critical values of the function, because it is at those points where the function has a chance of having a maximum or a minimum. Okay, now we will then in a later video extend this extreme values idea to the fact where you may have a boundary, and so you may want to look at the function. Does it have biggest values on the boundary of that region? But we're first going to just focus on the interior of the region. Okay, so here is how a typical problem could be phrased. Here is the definition of a critical point. It says an interior point of a domain. This is just a region where the function is defined. Let's look on the inside of that region. And a critical value is where both the partial derivatives are 0, aka the gradient of the function is equal to the 0 vector, and or where the partial derivatives do not exist. That's a critical point. So let's look at an example and see what can happen here. Let's look at an even problem. Okay, any function we should be able to try to find its critical values. And how many of them there are, I'm not exactly sure in this problem. Okay, so let's see if we can take a look and find the gradient. Okay, we know it's going to be the vector of first partial derivatives. So the partial with respect to x means y is a constant. So you'll get 5y from this term. This term, partial with respect to x, minus 14x. Partial with respect to x is 3. Partial with respect to x is 0. Partial with respect to 2 is 0. And now we go back through partial with respect to y. You get 5x. Partial with respect to y, 0. Partial with respect to y, 0. Partial with respect to y, negative 6. So essentially what we need to do is we need to solve the equations. 5y minus 14x plus 3 equal to 0, and the equation also has to be true that 5x minus 6 has to be equal to 0. Okay? So this actually is a pretty straightforward system of equations to solve. We can tell that 5x has to equal 6, which implies that x is equal to 6/5. Okay? And we can tell then that 5y minus 14 times 6/5 plus 3 has to equal to 0. So we can figure out that y is equal to 3 with a minus sign plus 14 times 6/5, and then divide all that by 5, and whatever number that comes out to be. Okay, so it looks like in this problem that there is only one critical value, and that is the value 6/5, comma, whatever that number comes out to be here. Okay, so this is your critical value. Okay, we can double check this problem. Just probably good to know how to double check some of your work. I like to, of course, use Mathematica. So we can put the function of two variables, 5 times x times y minus 7 times x squared. Now the functions that we ended up solving were pretty straightforward. Okay, let me make sure I've got this right. Plus 2x minus 6 times y plus 2. I think I've got the right equations now. Okay, and we can create, let's see, the slick way to do this is to take the derivative of the function with respect to the variables, take the derivative with respect to x and y, and there is your gradient vector. So the derivative of the function with respect to x and y. Okay. You can then set that equal to 0, 0, and I think we can solve this equation, system of equations for x and y. Let's see if this works. 6/5 for x, 69 over 25 for y. If we turn those to a decimal, we'll get 1.2 and 2.76. Okay, so there's your critical value. And what's interesting here is that if you plot this function, do a plot 3D of the function, we still don't know what kind of extreme value this is, but we know that some sort of extreme value has a chance at occurring at this point. So I'm going to plot this from 0 to say 2. I want to make sure that 1.2 is on the inside of the region that I'm about to draw out. So I'm going to lay out a rectangle around, let me see, 1 to 4. Okay, so there we can see, and now it's really hard to see. We don't get an obvious, what do you say? We don't get an obvious like problem that looks like a paraboloid. Can you kind of see that in one direction, as we've mentioned in previous videos with the second directional derivative, right? That in one direction the function is kind of going downward, it's bending down. But if you look at this from the other direction, can you see that it kind of makes a little upward bend here? I think that what we're going to find is that we have a saddle point at this critical value that we've just found. And the method of determining what kind of critical point we have is the role of the second derivative test. So I believe that at the critical value 6/5, 69 over 25, I believe we're going to have a saddle point. And that will be the point of the following videos.